It is Thursday, April 30th, and you are watching the Biotech Voyager. It's the place that covers what's happening next in biotech. Thank you so much for joining us. Jeff, how are you doing today?
Swell. I'm
Right
doing
on.
swell.
Sweet.
Super well. That's what swell stands for, right?
Yes, that's right. All right, man. It's been a busy last couple of days, especially in the lead up to ASGCT and ISCT as well. So lots of different companies that are releasing some very exciting early stage data. So we've got a lot to cover on the show today. And then just what we'll kind of put in the background for right now is that near the end of the show, if you're able to stick around for the entire 2 hours, we will be having John Boyce from 28 Capital to join us to provide his thoughts on kind of where the capital markets are moving inside of biotech. So stay tuned for that. We're looking forward to a good conversation with him to end the show today. But in between now and then, there's a lot to cover.
That there is lots of AI, more in vivo CAR T cell stuff. I can't escape it. It's just like going to be in my brain all the time now. Yeah, I'm looking forward to it. A lot of like a nice breath of fresh air when it comes to AI in medicine. There's an interesting story about AI imaging for surgeons that I thought would be really interesting to talk about. More in vivo CAR T cell stuff. And in reality, this is more of like a, hey, we've been blasted with like a bunch of new types of in vivo CAR T cell platforms, mainly from ASGCT releases and stuff like that. Okay, yeah, we're already getting this. So this is what I said. This is what I said. 2 hours. Yeah, we try and aim for 2 hours. You know, we think that the conversations are just so deep and contextual. There's too much texture to have only an hour.
Yes. So, you know, like you could, if you want to stay the whole time you can, or you can check back in, but
yeah,
you know,
and we're
the real ones stay the whole 2 hours.
Yeah, the real ones as in me and Ben. That's basically it, right? We're also going to be making like, 20-minute little segment videos that cover a certain topic that will be more like a little bit longer than a short, but not, this big, piece of meatloaf that you're not going to be able to finish. So we'll get you some nice bite-sized snacks. But anyways, so yeah, the in vivo CAR T cell stuff is mainly just from like, here's a bunch of different things we've been seeing recently. Let's talk about, are there any trends happening? Are there anything like interestingly new with any of these platforms? But then I'm glad that you picked this story, the cancer vaccine story, because I've been very like roller coastery up and down on cancer vaccines recently. And there's a bunch of different types of them. This is a DNA cancer vaccine thing we're going to talk about today. But we can kind of talk about like what a cancer vaccine even is, I guess, and like why they don't work usually, and how you can probably fix that. And then oncolytic viruses, which I thought were going to be a much more significantly prominent modality when I first kind of got into biotech and oncology. I was like, oh, this is a great idea. Turns out there's some problems that we can talk about, but the idea is still pretty cool. And I would even consider a company like kind of like Siren Bio as being a sort of oncolytic virus, even though it's not technically an oncolytic virus. And then Eli Lilly's got a big deal with ProFluent to do their AI-designed recombinase genetic editors, which I love this space too. And then finally, we'll get John Boyce on here to give us his the skinny on gene therapy.
Yeah, and then obviously on the Biotech Voyager over the last couple of days, we've published like something like 20 different articles, Jeff. So we aim to get through those.
Yeah, I think if we'll have plenty of time today. I would really encourage people to just like go and browse the website. All the articles are written by us. They're thoughtful and they're there. And we tend to, one of the biggest things that I want to make sure that I mention here is that we are trying to give a voice to the early stage biotech companies. And kind of be the voice from early stage, talking about how these seemingly small innovations can actually affect the bigger industry. So all of the things you're going to be reading on the Biotech Voyager, we'll say 90+%, is like super early stage stuff that you're probably not going to find anywhere else. So just go and browse. You'll find some gems, I promise.
Excellent. All right. So should we get started with AI imaging for surgeons, Jeff?
Yes.
Excellent.
We shall. Now I'm not
a bit outside
sure.
of the standard, a bit outside of our standard, but we're quite excited for this one.
Yeah. So let's just pop right into this. So basically, when you think of AI in biotech, at least for me, or let's say even AI in like imaging in therapy, immediately, probably more than half of us will go to like pathology. That's where I would think, right? Like we can give a bunch of, you know, I don't know, MRI images to a machine learning program, and then we can train it on how to detect breast cancer, right? And that's super great. No, I'm not trying to dog on that, but there's all kinds of other ways that AI is being used in imaging, and this one is super cool. I'm not super sure how like common this is, but what they're doing is they have an AI program that in real time interprets hyperspectral imaging, and it can
That's
give
wild.
surgeons in real time like AI generated analysis of hyperspectral imaging. What's hyperspectral imaging? Right? So this is the question that I had. I was like, okay, Hypervision surgical, cool. So now, Ben, this is just forgive my ignorance and my unculturedness. What exactly is this currency? It's not euro. I should know what this is.
It's pounds. Great Britain pounds.
Pounds. That's why they're in the UK. Okay. See, now again, I've never left North America, so just forgive me. I know what euros are. Okay, so they raise 17 million pounds, probably very similar to dollars, I'm going to guess. And they're using this to push the commercial line of this software, I think it is, into surgery for cancer, like cancer removal.
Right.
Now, I've got a video I want to show. They've got a really awesome video on their website that kind of shows how this works, because hyperspectral imaging is essentially a way of imaging that detects more than just like red, green, blue. It can detect things like, and it isn't just like temperature either. It can detect things, I don't even know how it does this, but it can detect things visually like tissue density, like oxygenation in certain tissues, like pH. But how do you know this? I have no idea. But then what Hypervision surgical stuff does is it will read this hyperspectral imaging in real time and just give like, here's a video of the surgeon's view of like the tumor, and like healthy tissue. And it can say, here's the tumor boundary based on tissue density and oxygenation and stuff like that. Here's an area of low oxygenation right here. Here's this and this and this. And it can help with, in my opinion, the big thing here, and at least in oncology, would be margins. Get tighter margins. We can save more healthy tissue. We're able to be more careful as we excise these things. I think that one of the most underappreciated aspects, at least like to molecular biologists who study cancer, one of the most underappreciated aspects of cancer metastasis is that the tissue disruption that happens during surgery can actually promote metastasis.
Yeah.
Hardcore.
I've got a very personal story of that. A in-law family member recently passed away due to that. Like 2 weeks ago, was completely fine, went in for gallbladder surgery, had the surgery, turned out the gallbladder had cancer in it, and the surgery basically just blasted all
like
the extra cancer tissue. Yeah, it just bursted everywhere. The cancer metastasized, and 2 weeks later, the person was gone.
Yeah. And it's one of those things where I guess you don't really think about it. Like if you were to ask a molecular biologist who studies cancer, what are the most common causes of cancer metastasis? It would be things like molecular things, right?
Yeah.
I'm not going to get into like the signaling pathways, but it's like, oh, this and this and this, and it would probably be molecular things. When in reality, it's like, well, I'm sure, again, I'm a molecular biologist, so I can't speak to the numbers, but I'm sure that a decent proportion of metastatic initiation events are due to surgery itself, which is kind of ironic and sad. Okay, so here is this video. It's 1 minute long. Hopefully the company doesn't copyright strike us. I don't know how this works, but I'm going to share my screen really quickly and show this thing to you guys, because it'll do a way better job at explaining it than I can, and it gives a little like picture of what it ends up looking like. So can I change this to this and then do remove? add my screen. Where are we? Here we go. Boom. Okay.
There we go. All right. I don't think we can hear anything, but.
Can you guys not hear this?
No.
Okay, well then basically what they're saying is intra operative surgery is based on what the surgeon can see with their own eyes.
Right.
That's why they have this picture of this woman's eyes here. Well, hyperspectral imaging can see things that the human eye can't see. Here we go. Here's where I want to get to. So here's like an image, just like a normal view of something in the body. I'm not super sure what this is. I'm not an anatomist, but here's this now. Bam. Here's
Whoa.
hyperspectral imaging. And then here would be like their software over top of it. And this is probably like a little bit of a more, obviously it's meant to represent what this thing can do for like a lay audience. So I'm sure that it's significantly more complex than this, but you can see things here. Like here's an area of low oxygen, needs investigation. I'm going to get rid of this banner real quick because it's got a, here's an area of high oxygen. There you go. Bam. And this is what it can do like in real time, and like you can see here, again, I'm not super sure how accurate this is like to the real world. It's just like for their video here, but you can see like the surgeons are seeing it in real time. Right.
That's wild.
Yeah.
No, hyperspectral imaging over the last couple of years inside of different applications, not just in biotech, but also above and beyond that into bioprocess, actually has some really exciting initiatives for sure.
Yeah. So again, I'm not like super familiar with hyperspectral imaging just in general, but I can definitely see how, depending on the things that you can detect, it would be a game changer. Can we find oil in the earth with this? we'll be billionaires.
I don't think it can go that deep, right? It's
right.
a fairly limited depth of understanding, but there are some really interesting applications of this kind of thing, of hyperspectral imaging inside of like agriculture, inside of like greenhouses, and even inside of different companies that may or may not be using plants to make biologics in different therapeutic applications
that rhyme with Bersium Biosciences.
But what's really interesting there is it actually allows you to basically look and characterize each individual leaf and see how it's doing, and measure a whole bunch of different parameters about the leaf in the context of the different environmental parameters and all of that different stuff. So it just gives you dozens of more parameters that you can then feed into this algorithm that's really looking to optimize how can we make the most possible of our product inside of this particular leaf. Gets really interesting fast.
So when did you, I've never heard of hyperspectral imaging. When did you first hear about this? Was it in the context of Cercium?
It was in the context of Cercium, yeah.
Of Cercium? Yeah. Okay, so it must be like a thing that people are aware of. I had no idea. And I think that this company, I'm not sure that they actually make like hyperspectral imaging like devices. I think that their whole thing is that they have actual software. Yeah, I'm wondering, maybe I'm wrong, because hyperspectral imaging is safe with our strong expertise in interventional imaging, AI, and medical devices. Oh, so they must do the whole thing.
Yeah.
We've designed I'm going to pull this up so I'm not talking to myself here. We have designed a intraoperative imaging system that seamlessly integrates into the surgical workflow and is capable of wide field, real-time, data-driven tissue characterization. What a sentence, yikes.
Yeah.
So objectively enhance the surgeon's ability to visualize and characterize, tissue no wonder they're getting pounds. Tissue intraoperatively without injecting any contrast agents, and no contrast agents too. That's huge. I wonder if they can do this in brain cancer. If they can do it in brain cancer, huge implications in like glioblastoma. One of the big things in glioblastoma. Here, let me give you a little bit of my in my postdoc. This would be huge, and if the company is watching, let me know if you can do this or not, because the big thing in like glioblastoma, and probably in a lot of different tumors, and also this is a thing that most cancer biologists don't think of: interstitial fluid flow, and fluid flow like in the tumor and stuff. Yeah. And I know for a fact it happens in brain cancer and probably in all kinds of other cancers too. But one of the big things in brain cancer is making sure that you actually get those margins. And in fact, brain cancer is probably the reason that it's so important in brain cancer is because it's very, 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 very important to preserve healthy tissue in the brain, right? Versus, maybe not so much in like the breast, right? Or so much in the skin. You can have relatively loose surgical margins, but in the brain, it's like we need to know exactly where this thing ends. Right.
Yeah.
And right now they're using things like MRI that relies on contrast dyes and things like that. And it's just like not super accurate from relatively speaking. And there's all kinds of like AI imaging softwares that rely on MRI data and things like that. And like fluid flow dynamics can help you determine where the boundaries may be and where to kind of cut a little bit more beyond the boundaries. But if they're saying that they can do this without any contrast agents in real time during surgery, if this can work on the brain, that's a game changer.
For sure.
That'd be so awesome.
But anyway, it's definitely an enablement layer for some of the different therapies that we typically cover. Super cool application of hyperspectral imaging, not just on the surgery side, but also on the potential production side as well, depending on your production mechanism.
Yeah, so that's very interesting.
Lots of stuff coming down the pipes there. Cool. All right. Well, should we move on to the cancer vaccine of the day?
Yes. So let's actually skip the in vivo CAR T roundup for now.
Yep.
I've definitely had enough of a vivo CAR T for a little bit. We can return to that. I definitely want to talk about cancer vaccines.
Yes.
Sure.
Cool. All right. Let's pull it up here.
Wow, we're getting so much better at this. Bam, bam, bam.
we have to change there we go. We'll change this as well. Okay.
There you go.
Yes. Okay. Yes. So this one's really exciting. I talked about this earlier this morning already on LinkedIn. Really cool because here you have an established cancer that's already getting treated with something like checkpoint inhibitors already. And the results are basically middle of the road. If you get diagnosed with advanced melanoma, you've got, basically a 50-50 shot whether or not checkpoint inhibitors are really going to work with you. And that's it, right? That's all you've kind of really got available to you. And where ScanCell has been able to come in is they have developed a cancer vaccine that provides a bunch of different targets here. So it's a DNA based cancer vaccine. It's designed to train T cells to recognize melanoma specific antigens, and it's used on top of the checkpoint inhibitors that are already used. So this is something that's being used on top of the established standard of care.
Yep.
And what ends up happening when you combine this on top of the established standard of care, you go from around 47%, I think it was.
I'm looking at it here. They got it's 43% in their phase 2.
So less than a 50% chance.
Or a checkpoint.
Yeah. So standard of care, 43% chance this is actually going to work.
And this was 43% for their progression-free survival at 20 months.
Right.
So versus the checkpoint inhibitor plus their ISCIB1 cancer vaccine went to 77%. So about a 34% increase in the PFS at 20 months.
Right. And again, guys, if there's anything else you want us to add in here, feel free to shout it out in the comments. But yeah, so we go from that, right? 43% chance of the standard
relapsing
therapy allowing you to have,
months.
of you relapsing within 20 months. When you add this on top, you go from 43% to 77%. That is absolutely nuts. Jeff, would you say that it deserves an applause? Yeah. There we go. Well done, ScanCell. Yes. Done.
Yeah. Now, again, these normal caveats here, right? Because it's not a head-to-head. It's phase 2, right? So like they're getting some efficacy signals. But it wasn't small. They've got N of 140 in these 2 different arms. And the thing about it too is like it really implies that checkpoint inhibitors alone, like you still there's still an issue with antigens.
Right.
There's still so if you give them the checkpoint inhibitors alone, sure, you can kind of release the brakes off the T cells, but something down there, they still need a target. Which is interesting. Did they get overall survival? I don't think so. I can go back and check the release. Their OS is expected later this year.
Right.
But yeah, it kind of hints this whole idea.
Yeah,
it's not.
Richard was just asking about that. Did they get
Yeah,
to
that's
OS?
why. Oh, I always forget to pull up the comments. Yeah, so they're gonna get overall
Thanks, Richard.
survival. It might be in there. The press release is linked in the ScanCell article that you're seeing here, so you can go and check the press release. The big thing too is they have fast track designation for this too, and I'm wondering that was the actual press release. They received fast track designation for ISCIB1 positive advanced melanoma. They're saying that they've got a 77% PSF or PFS at 20 months, and then their overall survival is expected in the first half of 2027.
Right.
So, but now I kind of want to have a little bit of a dialogue about cancer vaccines in general, because this data does show something interesting. And I'm sure that it's not, it's definitely not uncommon to combine a vaccine, RNA or DNA, with a checkpoint inhibitor. It's very, very, very common. It's just interesting to know that there's such a big jump when you add in that DNA vaccine, because it implies
basically a twofold jump.
Yeah, it goes up significantly, right? So it implies, so normally when I think of like the reason that checkpoint inhibitors work is because T cells begin to express PD-1, and that normally happens upon activation, kind of long-term activation. PD-1 expression is increased, and it's meant to act as a normal like braking system for our immune system.
Right.
The T cells that express PD-1 would likely have already been activated by antigen, right?
Right.
Then when you release the brakes by giving an anti-PD-1 or anti-PD-L1, wouldn't that antigen already have been giving them the eyes to see? Like, shouldn't those T cells already be kind of like primed against a certain antigen? And it seems like it's not really the case. And it kind of, this is more my academic brain being like, let's study what's happening down there, right? Like, is it, what's happening? There's all kinds of different possibilities. But I guess at the end of the day, yeah, obviously, antigen exposure via cancer vaccine plus checkpoint inhibitor equals better than either alone.
Right.
And it's a synergistic thing, it seems.
Well, I'd be curious to get your thoughts too, Jeff, right? Like, why is it that cancer vaccines have kind of not been as promising as they were initially conceived to be? Obviously, this is big news, right? But realistically, cancer vaccines have had a bit of a struggle over the past decade or so. This is a big change in terms of the direction, right?
Sure. It's a good sign for sure.
Yeah, it's a good sign. I'm curious, like, what really sets this apart from other cancer vaccines that have tried, in your opinion?
So I can tell you that the entire modality of cancer vaccines needs a bit of a reality check. Okay. When you think of vaccines, what do you think of? What kind of diseases are you thinking of when you think of vaccine?
You immediately think of infectious.
Exactly. And
Cancer's not
that
bad.
category of vaccine is prophylactic, right? So we're going to give my 19-month-old son, we're going to give him, MMR vaccine and all the different vaccines, and it's preemptively protecting him, right? So you give him a little shot, dink, and then your immune system can take a couple of weeks, maybe get those dendritic cells to take up that particle, get priming of T cells, lymph node activation, the whole 9 yards, and then you get a nice bolus of like memory cells and antibodies being formed. And then when in the future, could be 3 weeks from now, could be 30 years from now, when they're exposed to that antigen, let's say that chickenpox finally comes into my son's body, his immune system has been waiting for years for this, right?
Right.
So they're there, right? Exactly, Gardasil. So this is a perfect example of best of both worlds. Gardasil is a prophylactic vaccine against HPV related cancers.
Yeah.
right? And it's why it works. It's prophylactic, and you give it preemptively, and it can give your immune system the time it needs to kind of get that response going. A cancer vaccine is not given prophylactically, unless you're talking about Gardasil or maybe some other kind of like preventative vaccines, which I'm not really sure that there's any besides Gardasil or maybe a few handful of obscure other ones. But the majority of cancer vaccines are administered to cancer patients.
Right.
So let me ask you this, Ben. If my son was currently suffering from polio, would you give him the polio vaccine?
No, doesn't work.
No,
Too late.
you wouldn't give him the polio. Exactly. Why wouldn't it work? The reaction's already started, right?
Yeah.
And to get an immune response great enough to kind of stop that from happening, it's a different equation biologically than a prophylactic setting. It's the exact same thing with cancer vaccines. And not to mention Provenge. Okay, for sure. Is that also HPV though? Or is that some kind of like that's definitely not HPV. Let me see here. Okay, it's colorectal. What is the target there? It's prophylactic. And hopefully I'm conveying this idea, right?
Yeah.
It's meant to prevent future infections. A cancer vaccine is meant to stop, combat, and kill a current malignancy.
Yeah.
Different biological equations, different approaches. You need to have a significantly more robust initial response because you're not relying on the reactivation of memory cells to do the job. You're relying on the actual initial activation of those effector T cells and B cells, I guess, to go do the job. Yeah. And vaccines are just like not known to do that, really.
Yeah. No.
So I think, Ben, do you remember back in the day, like episode 1 or 2 of Bio to Bedside, when we were still doing the innovation in waiting?
Yes.
Segments, and I talked about shoot, I'm forgetting her name, but it's a professor I think at MIT who she had done a peptide vaccine for cancer conjugated to active C-gas sting, and they would infuse that, and then that would travel to the lymph nodes because it's humongous. It'd go to the lymph nodes, and it would simultaneously expose dendritic cells and APCs to the cancer antigen while also in giving them active sting. And that active sting is going to induce sting signaling, which helps the dendritic cells mature. It helps the general immunological environment to mature more quickly and more robustly, right?
Yeah.
And the whole idea is that the vaccine by itself is not going to induce a robust enough immune response to get any kind of anti-cancer effects. We need something else, right? And it's why you give vaccines with adjuvants, and normally like an adjuvant is like you can literally just give like dead bacterial particles and things like that to kind of freak out the immune system in the area and help the immunological response there. You need to have more a more like deliberate approach to get a really robust cancer specific, like really, really robust activity to get any kind of anti-cancer responses.
Right.
Now, so does that make sense?
So yeah. So how does that relate back to this story?
So it's interesting because this story here is a DNA-based vaccine, which in my opinion, if you're going to do a DNA-based vaccine, don't do it against one target. And I'm even wondering if they do. Like I don't know every protein in the body, right? So SCIB1, is that a single like protein? They're cancer vaccines, immunobody cancer. Oh, no. Give me 1 second here, because in my opinion, if you're going to do a DNA-based vaccine, you can just like string a bunch of different antigens along. Oh, epitopes from GP100 and TRP2. Okay, so it looks like there's 2 different antigens being encoded here. So basically with a DNA vaccine, what you can do is you encode little chunks of proteins in the DNA, when the antigen-presenting cell, like a dendritic cell, takes up that DNA, it will begin to transcribe and translate those little chunks of the peptides, and then it will present those chunks onto MHC to help activate T cells, right? If you get like a circular piece of DNA, just wrap that thing with 10 antigens, 12 antigens, right? And then you can get a bunch of different, a more complex response. The problem is like you need to know what the antigens could be, right? So it's like, how many cancers do we have where we literally know, the majority of patients share these 7 antigens? It isn't that common. What the field's going towards with like DNA-based vaccines is personalized, made in real time DNA vaccines, which kind of gets to your idea the other day about just gathering patients' tumors and just doing like tumor-wide sequencing, right? The benefits of doing that wouldn't necessarily be so much in like drug discovery and clinical trial optimization, but there is a lot to be said when it comes to personalized cancer vaccines. Because you can, if we can get the logistics down to where we can get patient's tumor is taken, sequenced, antigens are discovered, DNA vaccine is generated for that person, and then infused. If we can get that to happen in a timely fashion and have it cost effective, boom. So the reason that this is so important to me isn't necessarily like, oh, ScanCell's melanoma vaccine is so good. No, it's DNA-based vaccines plus checkpoint inhibitors are showing signs of life.
Right.
And if we can show signs of life in that space, that opens up an entire can of worms, I guess you could call it, for DNA-based personalized cancer vaccines plus checkpoint inhibitors.
Right.
Different story.
Gotcha. Yeah. So again, overall, really exciting news out of ScanCell, right? Where they have been able to essentially double the chances of progression-free survival at the 20-month point, and the FDA has appreciated this and given them fast-track designation. So huge congratulations to them. It's a big move, especially inside of the cancer vaccine space that hasn't quite got the recognition that it deserves. So we're excited to see where this goes into the future.
Mm-hmm.
Excellent. All right.
Oh, that's cool. So I'm just like looking at their thing right now, and it looks like I don't want to spend too much more time here. Okay. Oh, that's so cool. Okay. Yeah, this is okay. 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 What they're doing is they express what looks like an antibody.
Okay.
But the antibody is just like peppered with the different types of antigens. I don't know. And then like the cell will express the antibody and that gets processed. I don't know. It looks really cool. Anyways, go look into ScanCell's technology. It's like their immunobody DNA-based vaccines. It looks like it's more complex than just like DNA-based vaccines. Looks pretty
nice.
Cool.
Okay.
Anyways.
Excellent. All right. So oncolytic viruses, Jeff, since we're on the topic of cancer therapy.
Sure.
Right. I think that's
so.
You.
Yeah, so I think it is this one. So Theolytics. Now, this is just like an opportunity for us to talk about oncolytic viruses, okay? Because we how do I show this? ScanCell's massive. Oh, there we go. Do. Boom. Okay. So oncolytic viruses. And Theolytics has from what I can tell, a pretty significant differentiator, although I'm not super sure how differentiated it actually is.
Right.
Now, I'll cut to the chase. Theolytics is using an oncolytic virus, which normally just targets cancer cells, and it will get in there and just make them pop, basically. Instead of just targeting cancer cells, they're targeting cancer cells, but also cancer-associated fibroblasts.
Interesting.
That's the differentiation. So now not only does it target and kill cancer cells themselves, but it will also kill and destroy like the stromal fibroblast cells.
The structural components of this whole thing.
Yeah. Now, if you're in cancer biology, solid tumor biology, and I say, hey, we have a problem with cancer stroma. most people will think, oh, pancreatic cancer, right? Because it's like a hurt locker down there. You can't get anything in or out.
Right.
It's so packed with stroma. And this kind of gets to the limitation of oncolytic viruses. So the question for me was, okay, if they have this cancer-associated fibroblast targeting oncolytic virus, why not do it in pancreatic cancer? Right? They're doing it in ovarian cancer. The reason that they're not doing it in pancreatic cancer is because of a massive limitation of oncolytic viruses, which is most of them need to be intratumorally injected.
I see.
Right? So like, good luck doing an intratumoral injection in the pancreas.
Right.
That would probably cause more problems than it would solve.
Yes.
So instead, what Theolytics is doing is they do a intraperitoneal cavity, probably a spray, which is relatively common. And then that's where like ovarian cancer tends to live and metastasize anyway. So intraperitoneal injection, infusion, whatever you want to call it. And it does cancer cells and cancer-associated fibroblast destruction.
Gotcha.
Now, let me kind of pull up the specifics here. And again, I thought they dosed their first patient in a phase 1 clinical trial for oncolytic viruses. It's in collaboration with MD Anderson down in Texas.
Cool. Very interesting, right? Because if you kind of make the analogy of, like enemies within a castle, the standard approach is, well, just try to shoot down as many of the enemies as you can, or try to defeat enemies inside of the castle. And Theolytics is coming along and be like, hey, just a thought. We might be more effective in destroying the enemies inside of the castle if we start knocking down their walls and blowing up their bunkers,
right?
So that they aren't as effective as they could have been. So that's
other
really cool.
Exactly. And the other hidden benefit of this is that, because you wonder, okay, what is the point? What is the point of destroying cancer-associated fibroblasts if we're already destroying the cancer cells?
Yeah.
Right? Well, destroying the stroma will, one, allow for more oncolytic virus to penetrate deeper, in theory. It will also allow for deeper immune cell penetration. So if we start breaking down the walls, if we send an army in with some troops that will attack the castle walls, and then other troops that will attack like the people, right? As our troops start breaking down the walls, other battalions that we didn't even send in will also be able to penetrate deeper as well, right? And then on top of that, you can get natural immune cell infiltration. On top of that, you can get deeper drug penetration. Because drugs rely on two things to get into tumors: vessels and perfusion, right?
Yeah.
With more stroma, vasculature gets restricted. You get less like drugs in the actual highways, and then the drugs can't penetrate as deep through stroma as they can through like looser, less densely packed tissue. So knocking down the castle walls has all kinds of other benefits on top of just like getting your drug of choice in there.
It's actually kind of interesting. I wonder how well something like this would jive with Neob Therapeutics, right? Engineered bacteria that are going after kind of the cancer vasculature as well.
So the thing about Neob, and we actually, I think we did have some microbiome stuff.
I saw that. Yeah.
It isn't on the docket, but we're going to get to the microbiome stuff because there was 2 stories that hit for microbiome. And I guess Neob isn't microbiome in particular. They're like a bacteria-based therapeutic, but there's a couple of like live cell bacteria-based therapeutics for cancer that we're going to talk about today.
Nice.
What you're saying though, Ben, I think it's kind of like the opposite almost, because Neob exists because bacteria are known to be able to penetrate deeper into stroma because they're way smaller. They're like 100 times smaller than a normal cell. And if drugs rely on the vasculature and then just like natural perfusion, bacteria can actively crawl into places. And they're small enough to kind of get into little cracks and stuff. And what Neob is doing is they pack their stuff full of like tumor sensing circuits, and the bacteria will get to the tumor, and they love like highly acidic, hot areas, right? and they'll kind of like get in there, pack themselves real deep, crawl real deep into the tumor, and the Neob has programmed them to, once you get there and you kind of make up camp, start shooting out all kinds of drugs, right?
Right.
That's what Neob does. So it might help knocking the stroma down, but I think that Neob is kind of designed to not really care about the stroma.
Right. Okay.
Yeah.
Good to know. Awesome. But yeah, this is a really interesting approach. So yeah, kudos to Theolytics. We're excited to see where you go with this. Should be cool to watch. Oncolytics definitely as well. Kind of in the same vein of cancer vaccines, haven't gotten quite the comeuppance that perhaps they should have. So this is an exciting area to definitely be watching, right? CAR T, very, very exciting. Loads of attention on mAbs, but really when it comes to some of these different modalities that haven't quite hit their stride yet, cancer vaccines and oncolytic viruses are definitely due for a come up. So watch those.
Yeah. And they suffer from like very I guess like in hindsight kind of expected like limitations. One of the major ones is what they do is the viruses are replication competent, and they selectively infect, and then they are selectively like they have gene circuits that selectively become activated in cancer cells. So the idea is, if we can find one tumor, we can inject the one tumor, the virus will replicate like crazy and destroy that tumor while making more of itself, and then it can like go all over the place, and you'll get abscopal effects, right? I guess from what I understand, that hasn't played out biologically as well as we had hoped. So you're limited to cancers that you can actively reach easily, and then you rely heavily on abscopal, and both of those are just like limitations.
Yeah. Very good. All right, shall we move on, Jeff? I believe we've got Lilly's big bet on ProFluent next.
Oh, okay. This is also a great story. I'm having a field day today. And
Jeff,
I'll preface this by saying that the reason that I'm so excited to talk about this is because it kind of reminds me of one of my favorite cell therapy companies, Selectus. So we met Arthur. I think he's their chief business officer, potentially maybe their interim CFO. I don't know. He was like his position at Selectus was like not scientific upfront in nature. The dude blew me away. I mean, like, it was one of the most interesting, like, scientifically nuanced discussions in cell therapy I've ever heard. We met him at Advanced Therapies Week in Dallas.
Yes.
And this is totally off topic from like ProFluent, but it's when we go through this, I promise it connects. So what Lilly has done here is they're licensing some of ProFluent's AI designed recombinase genetic editors.
Right.
So how familiar are you with recombinase enzymes?
Recombinase enzymes. Just that they tend to be able to edit a larger portion than something like CRISPR can, right? We kind of like base editors, then CRISPR, then recombinases can edit a much larger section of genetic material, if I remember correctly.
Yeah, so their recombinases recombine stuff, right? And some of them work in different kinds of ways, but essentially what you get is ultimately at the end of the day, they are much more capable of like looping in bigger chunks of DNA, right? So you can use a recombinase enzyme to say, hey, we're going to edit this, 3.5 kilobase long section. That might be outside of the ballpark, but there's bigger chunks of DNA, which is great. And maybe I'll get to like the benefits of that, and I'll kind of put the cart before the horse here. The benefits of that is that you can use them to treat genetic diseases that are caused by a spectrum of different monogenic mutation or single nucleotide mutations. Yeah. So, for example, I think one of them I wrote a couple in here. I think it's things like oh my gosh, where did I write the names of the diseases in here? I went and I got a couple of examples. Okay, it doesn't really matter because the concept remains. I'm pretty sure it's like, oh dang it, I don't have it in here. Okay, here's the idea. Imagine we have a disease that is caused by one mutation in one gene, but that one mutation can be kind of anywhere in a big region. Like let's say we have an exon. And any mutation in this exon, it could be at the first nucleotide of the exon or the 1413th exon. And you get like a weird like little spectrum. Like some patients have it mutation here, some have it here, some have it here, but it's one mutation that it's single mutation per person, but it's a long, it could be a different, spectrum. To treat each person with like CRISPR, you need to know where that mutation is per person. Yeah. Basically. With recombinases, you can just say, doesn't matter where it is. It could be in this huge chunk of DNA. We'll just replace the whole thing with the wild type and whitewash a whole section so we can treat a huge slew of patients with the same thing, regardless of where their particular mutation is.
Right.
Bam. Now the problem, that sounds great. The problem with recombinases is that each recombinase enzyme is super, super picky with where it can actually bind in the genome. Whereas with CRISPR, you can have a single CRISPR enzyme, put it on a guide RNA and kind of bring it wherever you want, right? Recombinases don't have the same kind of like eyeball system.
Right.
They'll bind where the protein structure dictates, right? So if you wanted to say, hey, recombinase, can you please, pretty please with a cherry on top, bind right here for me? Recombinases go, no, make me, right? I'm gonna bind over there because I want to. If you want to have a recombinase enzyme bind right here and right here, you've got to meticulously design the recombinase enzyme itself from scratch, basically, and say, right, we're gonna make you bind here. That's what ProFluent's doing. They use AI programs to design recombinases that will bind to particular regions of the genome. And then you can say, okay, we want one to bind here, recombinase, flip in and then flip out the wild type gene, bam. That's what ProFluent's doing. And Lilly is taking full advantage. And ProFluent, fun fact, they use an AI program to do this. They call it Open CRISPR 1. It's open source.
Ooh.
They design, and this might not be the actual recombinase one, but they have a CRISPR design. And you can literally use this Open CRISPR 1 open source, like on GitHub. You can use their program to design CRISPRs, and then they have an LLM system to help you design guide RNAs.
Cool.
Right? That's their CRISPR. The recombinase might be a little bit more like tucked behind closed doors. But they're doing all kinds of really cool stuff over there, designing genetic editors from scratch using AI.
Cool. All right. So in the context of that, right? Like what have we got here? What is Lilly invested in? What have they grabbed from ProFluent?
I'm not super sure if they actually even like disclosed exactly like what Lilly is going to be taking.
Okay. But at a very minimum, then we could say that Lilly sees the benefit. They've seen some pretty cool data showcasing that you can use these really big recombinases to do some pretty cool gene editing.
Yeah, and Lilly probably has some ideas in house, and they were like, "This will solve these problems. Let's go talk." Because even in here it says, under the agreement, ProFluent will apply its AI models to design and optimize site-specific recombinases for multiple genomic targets. Lilly will receive an exclusive license to advance selected recombinases through in vivo research, preclinical development, and clinical studies and commercialization. So ProFluent will keep their program, but they're going to work with Eli Lilly to make some recombinases, and then Eli Lilly is going to take those recombinases and use them for genetic diseases.
Gotcha. Okay. Yeah. Nifty.
Pretty cool. Yeah. And just go and check out ProFluent's website.
Chef's kiss.
Yeah, nice.
One other thing I have seen, just even inside of the alternates to CRISPR kind of thing, right? When it comes to gene editing or gene insertion, would be like, do you remember Did you ever get to meet Jennifer Manning over at Como Biosciences?
No, but I've seen her on LinkedIn, so
Yeah,
I know I
they've
can
got
see
some
her face.
pretty big integrases, right? That you can take a
Okay.
very specific section of the genome and stick in a very, very large section of DNA. So I think that'll be a really interesting component of gene editing that's kind of outside of the darling of CRISPR as well to watch
Sure.
in the coming years. That'll be
Well, the
interesting.
thing is that in reality, CRISPR is the newest of all these.
Right.
CRISPR was like this big genetic revolution because we can finally just use a guide RNA to pull a like a nuclease around the genome. There's
Right.
companies. So I mentioned at the front that this reminds me of one of my favorite cell therapy companies, Cellectis, CELLICTIS. They're not doing recombinases. They're not doing integrases. They're not doing any of that. They use TALENs enzymes. TALENS, TALENs.
Okay.
And that's a different kind of genetic editing like enzyme. What Cellectis did is I don't think that they have that they probably have like AI machine learning stuff now. But I think in the beginning they were just doing screens and they had a big massive library of TALENs enzymes and they would know this TALENs cuts here. This one cuts here. This one cuts here. And they have like tens of thousands of them. And they can just say, hey, if we want to cut the genome here, we can use TALENs 8233A. And it will cut there, right? What ProFluent is doing is kind of like that library, probably more in silico, where we can say, we want to cut here. We're gonna make them bespoke from the ground, get a dozen candidates, and then go test it.
Nice. Super cool.
Yeah.
Awesome.
Yeah.
Well, should we switch gears here a little bit and go look at ADCs?
Yeah. Well, yes, sure. This is probably going to be kind of quick.
Yes.
Oh, this is the wrong one. Did I bring in the ADC one?
I've got that one. I've got it here.
Oh, you do? Okay, cool.
Yeah.
Oh, perfect.
Yes. All right. So I can take this one away.
Yeah.
So yeah, the problem that we kind of see inside of the cancer space, right, is that a lot of cancer therapies target proteins on tumor cells, and that leaves a fairly large blind spot. But there's another class of targets called tumor-associated carbohydrate antigens. Really big, really big mouthful. But these are the sugar structures on cancer cells. And they've got all sorts of really cool targets that you can go after as well. So instead of just kind of thinking, oh, I've got an antibody, I'm going to go attack a specific cancer protein, you can go after some of these very specific cancer glycans as well. They've been known about for years, but the challenge has been they're hard for the immune system to recognize. They're difficult to make in the lab, and antibodies against them have been tough to generate. All of that has been starting to change, especially over the last couple of years. So what Tacalyx has been able to do that is really impressive is they've built a platform to go after these sugar targets on cancer directly. And what they're doing differently is that they can synthetically create these TACAs. They can generate really high affinity antibodies, and then they can turn those into antibody drug conjugates. Really, really cool. So again, if you kind of thinking about this a slightly different way, right? All of the different cancer targets so far are kind of like making a wanted poster and saying, hey, this person is wearing a Blue Jays ball cap. And all you can ever look at for people are Blue Jays ball caps or different hats that they're wearing. And now that you've got sugar-associated antigens that you can go after, it's adding a completely different component, which is also, by the way, the person is also wearing a purple shirt in a crowd full of people wearing black shirts.
I'd even say, I love the analogy, and let's run with it. You ready?
Yep.
Normally, cancer therapeutics, if you want to use like the Blue Jays ball cap, is, hey, we've got a bunch of people over here who are all wearing ball caps. Most of them have black hats on, but some of them have bright blue hats on. Right. And you can just kind of look at the crowd and find the people, right?
Yeah.
But instead, now let's say they're all wearing Blue Jays caps, but a couple of them, the Blue Jays logo is the red on the Blue Jay is slightly more orange than everybody else's hat.
Yeah.
Right. Now, if you look at the crowd, you go, I can't tell who's wearing the slightly more orange blue, Blue Jay hat. Yeah. I can't tell. That's the subtle differences between these tumor-associated glycans and just like normal glycans. You can kind of see it on this picture here. The AI that makes these things is awesome because you can sort of see, if you look at like these little antibodies coming in, the branched stuff coming off of there are like the representation of these glycans.
Yeah.
A cancer-associated glycan can be 99% the same as a normal glycan with like maybe an extra like nitrogen chain on it, or like an extra little like carbohydrate chain here, right? And it's like very, 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 very subtle. The differences are very subtle compared to like the normal glycan on a normal cell. Distinguishing with an antibody between those two structural differences has been basically impossible.
Right.
So you can't really target them because the specificity of the antibody is just not there.
Yeah.
That's the major innovation. We're now able to synthetically make these things, optimize antibodies, and get like very, very, very specific antibodies. And then, we're essentially just saying, hey, we can now target this very specific TACA and not the normal glycan chain.
Yeah. Definitely. Yeah. So really cool to see. Yeah. They're opening up a new class of targets that most companies just couldn't access before. So anticipate, I would imagine in the future, some of these larger pharmas coming in and thinking, hey, maybe some of our bispecifics or trispecifics, we're going to add on a target for one of these tumor-associated carbohydrates. Right?
Yeah. Yeah. And I think also it opens up an entire like new modality of targets. And the question will then become, okay, if we can begin to target these things, what cancer types have we now opened up? Like does pancreatic cancer have a very specific glycan we can now target?
Yeah.
Probably. It might lead to significant advancements in cancer therapeutics.
Yeah. So yeah, I guess just quickly in terms of like the stage that Tacalyx is at, there are a couple other things just quickly to make note of. They are still a little bit early, but they have selected their first clinical candidate. They're moving through preclinical development right now. They're planning to file for human trials around 2027, and they've already raised 11 million euros. So that's pretty exciting. But yeah, again, this is going to open up a brand new component of what the field could go after. Anticipate pharma coming in and looking at some of these different tumor-associated carbohydrate antigens. And yeah, it could really improve tumor selectivity and move beyond the obvious targets that we've talked about previously on the show that everyone associates with cancer into the harder biology that people haven't been able to touch yet.
Absolutely.
Nice.
Absolutely. All
Sweet.
right. What do we got? Let's hold off on the in vivo CAR T stuff. We can probably spend a little bit of time. We'll go through the microbiome stuff and the bacteria stuff.
Yeah.
And then we can maybe like circle back to in vivo CAR T and just like pop through a couple websites, try and find some differences between these companies. There's so many like new ones coming out, which of course there is. Like I expected when, we got AbbVie, AstraZeneca, Gilead, Lilly, like everyone's buying these companies up like left and right. I was like, we're going to get a flood of in vivo CAR T cell companies now, either companies that weren't really doing it before, but now they're like, we do it too, or companies who were doing it and we're like, we'll remain stealth. And they're like, we're going public now. We're no longer stealth. So we're getting a lot of new in vivo CAR T cell stuff coming out. So we can maybe pop through a couple of the new ones that I've picked up. But before that, do you want to talk about some bacteria?
Yes, that would be great.
Cool. So let me try and find these two stories that came out recently. How's my volume, Ben? Is it okay?
Oh yeah, it's fine.
Nice. Okay. I had to turn my gain down because I watched back some of the videos and my voice was just so boomingly loud. But then I realized that my gain was at like maximum. So let's see. Microbiome Therapeutics. I know for a fact that there's two of them. Yep, there's two. Okay, here we go. Let's just share my screen here. Bam. Okay. So now that I know that this is pounds, 19 million pounds, 30 million euros, two different companies. Let's get into it. Let's get cracking. So Enterobiotics and mBiomics are these two companies. Two companies both using live bacteria, live attenuated bacteria, which means that they're not like pathogenic, they're non-pathogenic bacteria, for two very different things. And I'm actually not super sure how exactly these work. So if you want to go on a little journey with me, we can kind of figure out, they're definitely different. I have an idea as to how they work, but a lot of this stuff actually too is very mysterious. We're not really super sure how bacteria-based therapeutics work, especially like in cancer.
Right.
So the first one we can go into is Enterobiotics, Glasgow-based company. They closed $19 million pounds. I'm so American, dude. Immediately when I say a number and then $1 million just comes out. 19 million pounds for EBX 102. Okay, so they're in phase 2 for irritable bowel syndrome, essentially, like gastrointestinal disorders, which makes sense. Our intestinal tract is just loaded in bacteria. It's our microbiome, right? They help us digest food. They help to kind of modulate the immune system. It's very interesting, and there's whole like segments of healthcare that study and leverage the microbiome.
Yeah.
Now, I'm not super sure exactly how a live oral bacteria-based biotherapeutic would do anything in irritable bowel syndrome, other than
that is kind of the most direct method.
Well, here's my thinking, right? It's just going to be some kind of immunosuppressant in the gut, essentially. That's how it will work, right? Like I'm unfamiliar with how these things actually work in there. So irritable bowel syndrome, other kind of like inflammatory gut intestinal disorders. If you have a bacterial therapeutic, I'm going to guess it's just like going to be immunosuppressive.
Right.
Right. So let's see if my look has run out. Boo, 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 boo. Would you look at that? Let's see. Do they even talk about how it works?
I think you did before, just in like that, in the Google summary when you first looked at it.
Oh, did it?
I think so.
Okay, so a full spectrum microbiome therapeutic developed by Enterobiotics to treat irritable bowel syndrome by restoring gut bacterial diversity. Interesting. But the question becomes, how does the restoration of gut bacterial diversity treat irritable bowel syndrome?
Well, I would imagine, right? Like with something like that, they've probably identified some different bacterial populations that are commonly associated with common bacterial health, and they're downregulated in irritable bowel syndrome. And so restoring back in those populations is going to be healthy. That's actually been used in some other applications as well, with I think like cancer, where I remember
we're getting
years and years ago, right? Like you have a certain type of environment of bacteria that are preventing bowel cancer, that's preventing bowel cancer from being effective. Preventing bowel cancer treatments from being effective. It's progressing, and by injecting like sterilized samples of other people's microbiome flora, it actually helps with patient
How do you
outcomes.
do that, Ben? I first heard about stool transplants, and I was like, I'm sorry, what? A stool transplant? It's nice and sterile. It's actually not sterile. It's not. It's not. It's actually meant to not be sterile, but they put it in a capsule and you take it. But you are like literally eating somebody else's poop. That's basically how it works.
I mean, if you've got to choose between that and death,
dying of cancer,
I will take a pill and just not think about it again.
I will eat someone's poop to treat my cancer if it will work. But I think the point that I'm making is that mechanistically, it's still relatively mysterious. Like you can easily say, hey, there's this correlative, trend that people with IBS tend to have a overrepresentation of certain bacterial strains and an underrepresentation of other bacterial strains. Maybe if we, kind of level those out, that could be playing the disproportionality of their microbiome might be playing a role in IBS progression. If we balance it out, can we affect that in any way? And the answer seems to be, let's just see if it works. And and not so much like let's deliberately like have this certain strain or this certain strain. But there are some there are some platforms that do know, like we know that this kind of bacteria, when you have more of it, you tend to have more robust immune responses against cancer, and they'll try and kind of infuse you with those kinds of a method to increase that aspect of your flora. And I think that that's kind of what mBiomics is doing. So basically, Enterobiotics is saying we're just going to help restore your natural gut flora, and that's going to help mediate IBS symptoms, right? Or moderate IBS symptoms.
Cool.
mBiomics, this is completely different. And if I'm remembering correctly, they're doing it not even for like GI cancer, it's for melanoma.
Cool.
Yeah. So the idea behind mBiomics is completely different than anything that has to do with the gut, right? They're not chasing a GI indication. They're going after melanoma, banking on the now well-documented finding that gut composition can actually shape how people respond to immunotherapy as a whole, really.
Yeah.
So when I was in my PhD at Roswell, one of the big things that a whole department was studying was the interaction of the gut microbiome with your immune system, right?
Right.
And there's also a lot to do with, or a lot to be said about the differences in your microbiome can actually affect the bacteria composition of a tumor, because that was a big finding too. This also goes to Neob as well. The idea that we had an idea that like tissues were relatively sterile, like non-GI tissues were relatively sterile, which would mean that a non-GI cancer would be relatively sterile.
Nope.
Turns out not the case. Turns out not the case big time. There's a lot to be said about your gut composition resulting in a change in the microbiome of your tumor, if we can call it that, and how that can impact cancer therapeutics. So if I had to guess, mBiomics has a more targeted approach. Now I don't know what these people are doing. So let's go to see if this is like an actual like strain of bacteria. mBiomics. Let's just go to their website maybe. Okay, here we go. An incredible opportunity for therapeutics. LBPs, live. Anything on their actual, proprietary strain library, co-culturing, manufacturing, analytics. Yeah, see, this is much more deliberate. You see what I mean? This is much less like, let's just give you a bunch of different strains to try and re-establish your normal flora. This is like, we need to know exactly the kind of composition we need to give you to give. Yep.
Yeah. As opposed to kind of before, it was just like, oh, well, here's a healthy person's fauna. Well, let's give you some of that. This is very much like, hey, no, these are like the 50 different things that you need right now. We're going to deliver that very specifically to you. Boom.
Exactly.
Let's go.
Yeah. And unfortunately here, they don't really give a whole lot of details on their website, which is, to be expected, but it does seem like it's a lot of discovery, figuring out exactly like these different types of correlative, it's mostly correlative at this point. Because again, the what exactly it's doing, normally it has to do with metabolism. Normally, like these bacterial strains will produce some sort of metabolite that can be immunosuppressive, pro-cancer, anti-tumorigenic, So, yeah, it's really, really interesting. And it is one of those things where you tend to think it gets a little bit uncomfortable because you realize, like, there's a lot of bacteria on me. We are like incubators to a certain extent. We're not. There's a whole ecosystem of living organisms that are living in us, and we can leverage them for therapeutics.
Yeah,
pretty good,
including bacteria. Cool. All right, awesome. Should we finally just bite the bullet, Jeff, and let's look at in vivo?
Let's crack it open. So let me pull up the
And folks, at this point, right, if you have any news that we don't cover or anything you'd like to see highlighted with regards to in vivo CAR T, let us know, and we can direct our conversation at this point. At this point, we've gotten through most of the main stories that we want to get to. While we're still waiting for John Boyce, who will be coming at 12:45. Stick around for that. But in the meantime, right, if you have any other stories that you would like to see highlighted or you'd like to get us to provide some commentary on, feel free to let us know in the comments, because now we're kind of entering somewhat unstructured time of the show where we're going to take a look at just all of the different stuff that's been happening inside of the in vivo space for CAR T.
Yeah, let's just have a chat about it. Let's just chat. Let's see. So here's the article that I published this morning.
Yeah.
And it kind of goes through all of the different signals that we have seen come in the Biotech Voyager regarding in vivo CAR T over the past week or two, right? So it starts on April 13th was kind of the first thing. Although this was a little bit of a stretch. Really, it's April 20th with Immunofoco. Then we covered Create Biomedicines. They're doing that in vivo CAR immune cell platform, right? That I mentioned. And then Sale Biomedicines. We may have talked about Sale a little bit. They have their engineered RNA, eRNA based CAR T cell program. And then just yesterday, Chinese company Vivacta that's coming out of Grit Bio. Grit Bio, I think Grit Bio used to be like a DNA based cancer vaccine company. We'll look into it. And then ME Therapeutics. And the reason that I didn't, or this one's pretty cool too. It's a dual targeting in vivo CAR, which this is going to get to one of the major innovations that I'm going to expect with in vivo CAR. So maybe we can probably start there. You want to start here with the ME Therapeutics?
Sure.
Because one of the biggest problems with in vivo CAR T cells that I'm going to anticipate is, or let's put it this way, when you look at allogeneic CAR T cells, the allogeneic CAR T cell therapy companies' favorite thing to do is edit the heck out of their cells.
Yeah.
And some of it's required. You need to stealth them. You got to delete the TCR. You got to delete HLA normally to make them stealthy. You got to express some kind of NK cell inhibitor or some kind of stealthing technology. A lot of it's required. But then you look at companies, Kiragen. Remember Kiragen? You know Kiragen.
Of course.
Kiragen.
Shout out Aaron. Yeah.
Aaron Edwards. Their big thing is their whole shtick is kind of on the same thesis where they've noticed a lot of allogeneic CAR T cell companies just edit their cells beyond belief. And Kiragen is saying, what if we didn't edit them to express things like switch receptors and different stuff? We just deleted stuff. We can delete TGF beta receptor. We can delete SERP alpha. We can delete certain inhibitory molecules to make them resistant to immunosuppression. The reason that I'm mentioning all this is because these companies make these edits because it makes the cells better at killing cancer.
Right.
The problem with in vivo CAR T is that it's going to be so hard to do multi-edit in vivo CAR T.
Right.
Just because of payload capacity limitations.
Yeah.
Right? So if you want to have your in vivo CAR T have a switch receptor and, some kind of co-stimulatory thing, I don't know, you just can't do it. You just can't do it. You can express a CAR. That's it. Right? I'm waiting for the day where we have armored in vivo CAR. That's what I'm waiting for. Multigenic in vivo CAR.
Right. That's going to be pretty difficult.
It will be. But this is kind of sort of leaning in that direction. They have a multi-antigenic, multi-targeting in vivo CAR T, or in vivo CAR M. I don't know. It's a CD19 and CD20 targeting.
Super cool.
Oh no, targeting CD22. I'll have to go back and check what this is talking about here because. Wait a minute. Hang on. This is in vivo CAR M. Why did I miss something up here? Oh, they must have both. That's interesting. Okay.
Regardless, in vivo immune cell therapies as opposed to just in vivo CAR T.
Yeah. But they must have a dual targeting one too, because whatever, it doesn't matter. But this even this is different, right? It's a myeloid targeting therapeutic, or a in vivo CAR M, which I don't know. After the failures of Charisma, which they had their CAR M platform, I'm a little bit down on the myeloid cell therapies right now.
Right.
So we'll see where that goes. But anyways, the point that I kind of wanted to mention here is that we're getting a lot of innovation in the in vivo CAR space. It's no longer just an in vivo CAR targeting CD19 for B cell depletion. We're getting the same kind of sort of innovation that we're seeing in like the ex vivo CAR space in the in vivo, which is completely expected, and it's honestly what I'm excited for. I'm excited to see the genetic innovations that come out of this, because there is an arms race for CAR T cells for those genetic edits. So if we have that arms race being applied to the in vivo space, it's going to ramp up our ability, like the technology that's made during that arms race will ramp up our ability for other genetic medicines.
Definitely. And the ability for that to, on top, be ultimately benefiting the patients, because we are able to make something that's a bit less personalized and can be deployed at a much higher scale than current approaches for personalized ex vivo cell therapy applications.
Yeah, that's the whole pitch with in vivo. We can do it faster, we can do it cheaper, we can do it more consistently. I think it's I think it's a little bit too good to be true. And if we do have some time here, I don't know if you want to. We could kind of duke it out about in vivo CAR T a little bit, I guess. But what do you want to focus on here? Do you want anything in particular?
Well, yeah, I think it would be interesting, like if we just basically go one by one very quickly, almost like a lightning round. What were like if we keep this graphic up here, but we just kind of lightning round go through that article, right?
Mm-hmm.
What were those key components? What were these key milestones that came out that have really just kind of been a rip for in vivo over the last couple of weeks?
So a lot of it's preclinical for ASGCT. I'll get that out of the way immediately. It's more like, hey, look at our stuff. We have one too, right? So like, for example, Immunofoco presented preclinical data on their lead program, IMV-102. It's an in vivo BCMA targeting CAR T. BCMA probably for multiple myeloma. Potentially, maybe not. B cells. Yeah, it's multiple myeloma. The cool thing with Immunofoco is that they've already got a phase 3 ex vivo CAR T, and they're like, we're going to do in vivo too, because in vivo is winning right now. Yeah. So Immunofoco, and then Create Biomedicines. We went through them. They dosed their first patient with a first-in-class multi-immune in vivo CAR for HER2 solid tumors. That might be that's one of the first ones that I've seen for like a solid tumor. So Create Biomedicines used to be called Myeloid Therapeutics, and they've got an in vivo CAR T, CAR NK, CAR M, like simultaneous in vivo platform targeting HER2. That's like super innovative, actually.
And this is Create
Medicines. Yeah, they dosed their first patient with MT304.
Yeah. So ideally, we've been having some chats behind the scenes. We should have the CEO of Create on next week.
Ooh, yeah, that sounds fun.
Come back for that.
And then on the 27th, Sale Biomedicines reported non-human primate data showing in vivo CAR T B-cell depletion across blood, bone marrow. This Sale Biomedicines, they had the engineered RNA, the eRNA. Right. And their whole thing was, with the engineered RNA, they've included iris regions, the internal ribosomal entry sites, to have more reliable and more robust translation of the mRNA.
Right.
Which should result in more persistent and more robust CAR expression on their T cells. And that's when I was wondering, like, is that a problem? Was the lack of persistence of the CAR expression or not robust, lack of like robust expression a problem? Since then, I've done some research and it turns out, yep, it is. Now, Ben, what is one of the other benefits of doing ex vivo CAR T cell production? What do you get to do before you kind of send the therapeutic off to be put in the patient?
Well, QC is nice. Making
Quality.
sure that you, yeah,
Precisely. You can run all kinds of standards for your QC, right? One of those for CAR T is CAR expression. We want to have like 97% CAR expression, or we want to have a certain level of CAR expression in our T cells. You don't get that with in vivo. You get what you get, and you don't pitch a fit, right?
Yeah.
That's one of the issues. So in implementing a reliable way to improve the CAR expression and get more robust CAR expression actually is a significant challenge to overcome in vivo CAR. So like I said, I have no issues with in vivo CAR in principle. I had issues with the hype of version 1.
Right.
Version 1 was more of like an anomaly or a novelty. You can say, oh my gosh, that's a cool idea. We're going to have to improve. Right. But immediately it was like Lilly, AstraZeneca, Gilead, everyone's buying these things. And I'm like, you're going to have to do a lot of improvement. What we're seeing here with all these different innovations is the innovative layer on top of version 1.
Right. Yeah. Agreed. Yeah. It'll, again, like what I am to some extent just still holding out on is, to what extent are you going to have a significant portion of the cell population that you're attempting to target, be that T cells, macrophages, what have you? How are you making sure that you hit enough of those that they're and then they are receiving the payload properly, and then they are activating and actually going and doing their job? Like, maybe I'm missing something, but that still seems like just such a massive challenge to get done. Obviously, people have been able to do it inside of gene therapy for other applications, but when you've got something that's this mobile, it leaves a little bit to be desired. We shall see.
Yeah, and I think that it's probably we are going to. I'll make a prediction, low-hanging fruit prediction. We will get the first positive signs of commercialization of in vivo CAR T in autoimmunity. It ain't going to happen in oncology, guys. That's my prediction.
All right,
it's not going to happen in oncology anytime soon. The first big win in vivo CAR will be in autoimmunity. It makes way more sense in autoimmunity than it does in oncology. Cancer is too big of a beast to leave up to that kind of, like, the limitations of in vivo CAR T are the perfect weaknesses that allow cancer to escape. With autoimmunity, you're not trying to outrun a massively expanding bolus of immunosuppressive B cells. Right. You're trying to eliminate the normal B cells, and they're not immunosuppressive. They're not rapidly dividing to the extent that a cancer population would be. There's no real issues with like having to keep persistence of the T cells. You can have a B cell depletion in 7 days, and then the T cells can go away and it's fine. You get immune reset. In hematological malignancies, if you leave 100 of those cancer cells, odds are it's going to come back. You need to have, and it needs to be like, you got to have constant surveillance, a thing that in vivo CAR has not shown to be able to do, especially the RNA-based ones. RNA-based ones, forget it in oncology. Never, never, never.
People are going to get mad at you for that one.
Fight me. I do not care. Now, there are a lot of like lentivirus-based. There's lentivirus-based in vivo CAR T that's going. Yeah. The challenges with that is off-target infection. What do you do with that? You're going to have permanent integration of a CAR in like your heart muscle, potentially. Like, that's not going to be good. Yeah. So, yeah, it's just there are a lot of nuances, let's say.
Fair enough. Yeah. All right. So I guess again we've not happening.
What?
All right, sweet. All right. So again, we're gonna have John Boyce coming on 12:45 to talk about where he sees the puck going inside of biotech. He's spent a lot of time inside of the investment space. Really looking forward to that conversation coming up in about 20 minutes or so. In the meantime, Jeff, we do have a couple other stories that we do have in the wings here. One that I can take over, just with regards to. Let me bring it up here. T-Rex Bio.
I was gonna pull that one up too. There you go.
Right on. Okay. So let's have a chat. Well, let's talk about T-Rex Bio here for a second. Sound like a plan?
Do it to it.
Okay, sweet. Yeah, T-Rex Bio is an interesting one. We've been spending quite a bit of time this week talking about T-Regs, and then their company is called T-Rex. We see you. That's a great name. And then you can go even further meta, where it's like, well, actually, T-Regs don't behave like a T-Rex at all. It's kind of the opposite.
They're the opposite. Now, I have one little piece of like biotech gripe. This is one character off from Trix Bio.
Yep.
Come on, guys. We gotta. I get that it's like, it's T-Rex and Trix, not close in pronunciation, but databases will have a tough time with these kinds of things. But yeah, I love the play on that. People in the T-Reg space seem to like the word T-Reg. They want you to know we have T-Regs, just so you know. It's in the name.
Excellent. Okay, so let's just quickly kind of go through what makes this important. So again, kind of the overall problem here is they're going after atopic dermatitis, which is driven by an overreactive immune response in the skin. So there are already some treatments, but they have limits. They don't respond well long term. There's side effects. Most therapies are just suppressing the immune system broadly. So you have all sorts of knock-on effects where it's like, okay, my skin is no longer irritable, but I'm immunocompromised and open to a whole bunch of other stuff. So where T-Rex is coming in, right, is they are going to be focusing on, instead of suppressing the immune system, they're restoring balance, which T-Regs are known for doing. So their drug is targeting a receptor called TNFR2, which specifically activates the regulatory T cells, the Tregs that we've been spending so much time talking about. And so obviously Tregs naturally will calm down the immune response. And so by doing so, this allows you to locally repress tissues in the skin, right? You can start to get much more specific. Instead of broad immunosuppression, you can get a lot more localized, and it avoids activating other immune cells like NK cells or effector T cells, that sort of thing. So it's early, but they've already been able to dose their first patient. They're in phase 1A, phase 1B clinical trials. And yeah, they've been able to see some expansion of regulatory T cells inside of folks without triggering that broader immune activation, while also allowing for a therapeutic benefit as well. So interesting to see. Tregs don't get as much love or attention perhaps as they should, but there are a lot of diseases and indications that they can go after that they are very well suited for, that other standard T cell therapies might not be as good at.
So this isn't a Treg cell therapy. It's a TNFR2 like small molecule agonist.
Yes,
essentially.
Yeah, it's activating the Tregs. Yeah.
I wonder if they've got like Treg cell therapies, or if they're just designing. Because the thing is like, okay, sure. I mean, there's other like immunosuppressive agents that it's kind of like a targeted immunosuppressive therapeutic almost.
Right.
But I'm wondering if they have actual cell therapies, or if it's just the small molecules, or some kind of like peptide-based receptor agonist. But yeah, basically what they're saying, what they're banking on, the inflammation is better treated by limiting the expansion of Tregs versus limiting the release of cytokines by Tregs. Or sorry, they're banking on creating more Tregs will be
Yes.
better than promoting the expression and secretion of immunosuppressive cytokines from the Tregs.
Right. Yeah.
Yeah. So it looks like a novel TNFR2 selective agonist designed to activate and expand effector Tregs in AD, not to be confused with Alzheimer's disease.
Yeah.
Yeah, and this is their first clinical trial, and it was that they got their first patient dosed. Yep, this week dosed the first patient in phase 1B the phase 1B, so the expansion portion. Nice. Okay, cool. And all on atopic dermatitis.
Yeah.
See, it's these kinds of things that there's cool biology happening everywhere. You just don't know it. I never would have thought, like, let's look at a TNFR2 agonist for atopic dermatitis. It's like, how about we don't do that? But then you realize it is cool biology.
Yeah.
Biology is so cool, man. This industry is so cool. I've got a brother who works in like software engineering. Biotech, we are so privileged in biotech. The industry is like so awesome. There's like, even to have these companies with the cute little names and the logos and like their little branding. It's like playing for a sports team. It's so much fun.
Definitely. Cool. All right. It's interesting that they are. Yeah. The interesting thing here, right? The one thing I didn't pick up is this like an intravenous injection, or is this like applied as like a topical
an oral
cream? Or is it an oral thing?
Oh man, that's interesting. I wonder, when it comes to atopic dermatitis,
Right.
Is it localized enough to just be a cream, or would it need to be like a, let's see.
Because if it's cream, that's nifty.
Yeah, who was the people that you talked to at Moffitt who were doing like a cream based thing for melanoma or skin cancer?
I feel awkward on air. Just a section. I'll have that name for you in one moment.
Because they had a cool thing too, right? Where they were doing like, their technology was to help actually deliver the therapeutics via topical treatment. There are other like topical.
Ryan Beal, shout out Ryan Beal over at Dive Biosciences. Yeah, they've got something really cool.
Yeah.
So it's like buffering agents that can be delivered directly through the skin, and then those buffering agents will specifically go to cancer tumors, and using just kind of like basic osmosis technology, basic osmosis chemistry rather, come in and essentially balance out the tumor acidity, which recruits more of the immune system in.
So this is a biologic. T-Rex's TNFR2 agonist it's probably like a specific formulation of TNF that will bind to TNF receptor 2. It's delivered via subcutaneous injection.
Cool.
So interesting. Just like directly into like the actual
like
patch of dermatitis, or is it just like anywhere?
I would imagine it's probably like the specific part of dermatitis, right? Because if it's a biologic, it's not a homing molecule, right? So it's not going to just naturally go to where there's going to be Tregs, right?
Yeah.
Like you probably have to inject it locally, and that's going to get it inside of the Tregs.
Yeah, I would imagine that sites of inflammation probably have a larger bolus of just like Tregs kind of around. Even though there's inflammation, there's probably just like more immune cells there. So if you were a systemic therapeutic would selectively work at those sites, just like based on population distribution. But I'm wondering, like, I just don't know a lot about atopic dermatitis, if it's just like you get like patches all over the place and you need to do like injections everywhere, or if it's normally just like one spot.
Right.
I don't know.
Yeah.
I don't know. Anyways, biology is cool.
It certainly is. All right. Jeff, again, folks, in about 10 minutes or so, we're going to have John Boyce on, the managing director of and co-founder of 28 Capital, that invests into early stage biotechnologies. Very excited to have a conversation with him. So stick around for that. Coming up in about 10 minutes. Today already, we've been able to get through a lot of different shows. We've been able to talk about in vivo CAR T. We've been able to go through some really cool applications of spectral imaging for surgery. We've been able to look at ADCs that are going after brand new cancer targets in the glycan regions that we've never seen before.
Brand spanking new.
brand spanking new. So there's been a lot going on in the last couple days. Also, just for people who will be attending, I'll be at ASGCT not this week, but the week thereafter.
Boo.
Jeff has
I will
opted
not be
not to
attending.
come.
I'll be in Myrtle Beach. So how's that? Put that in your pipe.
Fair enough. Myrtle Beach sounds lovely. But yeah, as in case no one has figured this out yet, maybe I'll put it in the chat for people to take a look at themselves. My understanding was, oh shoot, the problem with the ASGCT article with all of the abstract is it's just this massive PDF that you have a really difficult time getting through because it's 3,500 pages long. As it turns out, there is a web search version that ASGCT provides that I missed like the first couple times when I was on the website. So maybe I can just stick it in the chat here, and you guys can take a look at it, because it's actually a pretty interesting application. It's definitely going to make your life a bit easier. I'll put it in the chat here on LinkedIn, and then maybe I can put it in the chat on in the normal chat here as well. But yeah, keep an eye on that. It'll definitely help your life if you're trying to get through all those different abstracts. Cool.
All right, Ben, hit me with it.
All right. Yes. So this is not exactly an early stage biotech signal, but this is the final thing that we'll probably talk about before John Boyce comes on, and actually might be a nice transition. In case you guys missed this is massive news. This can't really be like overstated enough. I'm pretty convinced this might be one of the most transformative things that's happened in the last like decade inside of the regulatory
I think it's
space.
the biggest story of the year, at least.
Yeah.
Of the year so far, at least.
Yeah. The fact that the FDA is switching from a system that worked really well 50 years ago, because we didn't have the internet and we didn't have a thing called a dashboard that lived on a computer.
This thing called software.
This thing called software. This is huge. And so obviously everybody has been talking about it, but the fact that the FDA has launched real-time clinical trials is pretty crazy. So instead of you having all of your data and it's living on random computers at your CRO or at your CDMO, the new requirement is going to be that the FDA will basically have you in real time uploading all of your data into the cloud. That gets synthesized, and then the FDA reviewers who are assigned to your case see your data as it is coming in. And so the reason why this is such a huge deal is, at this point, and I watched a video where Marty McCary was going through this, he was saying there is such a huge amount of the clinical trial timeline that is just waiting.
Oh.
Waiting. So
I mean, you of course.
Right? And he's saying it's up to 45% of the time of that clinical trial timeline is just waiting. So either the FDA waiting for you to assemble your data, or for you waiting for the FDA to get back to you about the data that you've submitted. A big chunk of that is just kind of the administrative wait time. And so
Ben,
they estimate...
I've never been involved in a clinical trial myself. Do you have any idea what would be like? I mean, obviously I'm not sitting here being like, what would the benefit be? But give me some examples. Like, what would... I'm very unfamiliar with like the clinical trial space, to be totally honest with you. I understand what they are, obviously. Like the technicalities of it.
Yeah. It basically eliminates the wait, like just waiting. It eliminates the paperwork component, which is just such a labor-intensive, time-intensive component of clinical trials. Instead, all of your data just automatically goes to the FDA. It gets synthesized, put into a dashboard for the FDA reviewers to look at, and they see it in real time, which means the turnaround time is that much faster, because there's not 6 million different forms that you've got to fill in before you submit this data to the FDA. And then they look at it, figure out, and then get back to you. This comes in and says, guys, turns out we saw your data that you uploaded yesterday morning. Looks good. Well done. Keep going. As opposed to kind of just this outdated notion of, like getting all of that paperwork assembled, that taking time, a lot of different people, you've got to pay a lot of money to submit that stuff. It's just automatically going to the FDA.
There's
and
no. So this is the first time that they've implemented any kind of like real-time data entry for clinical trials ever.
As far as I can tell, and people can sound off in the comments and tell me if I'm wrong, but that's the wild part. Yeah.
So how else would it be done? Like horse and buggy? What was happening before this?
Well,
like,
I
so
mean,
you'd upload data into a system, and then what?
so
I
either
don't know. I guess I'm missing something.
You would submit like all of the files and the forms in a very specific way to the FDA, either on paper or through, an email or some sort of submission service.
Like a submission thing where it's like, hey, we've finished dosing our patients, we have all of the data, it's sitting on our hard drive, now we're going to have a big like mass upload to some system 6 months after the patients have been being dosed and everything. Okay, sure.
So what the FDA is literally working with some pilot companies on right now is, as you receive the data, like there's built-in systems that, like, as the data is received, that data just goes directly to the FDA. There's like not really the details are still a little bit aren't fully elucidated yet, but basically there's not that middleman step of taking the data, sitting down with it, extracting it, maybe hiding bad data 60 pages deep so it's harder for the FDA to see. Just kind of like the raw data is going directly to the FDA.
And then this will like expedite recommendations for moving forward.
Exactly.
I'm going to guess.
Yeah. So it's good on two different ways, right? If the drug if the drug isn't safe, if an adverse event occurs, or one of your clinical patients has a fever, that data goes directly to the FDA. Like it's linked in the cloud, so they see the data that's coming from your clinical patients as you see the data coming from your clinical patients. And it just allows them in two different ways. First of all, to act a lot faster in case they need to shut the trial down. But if you've got a bunch of really good data, move forward as quickly as possible. So I see that it's really as like an interesting, not rebuke, but like an interesting response to the to kind of other regulatory bodies around the world really starting to become competitive in a lot of different ways. This, in my view, really cements the FDA back on top if they can pull it off and they make it work. Obviously, there's still challenges in this. We'll like there will be there will be wrinkles to be ironed out. But I am interested in this, and I'd be curious for anyone else who's watching, if you have any thoughts on this. Feel free to modulate my take as a Canadian in the situation who's kind of somewhat frustrated, being like, "Come on, Health Canada, do something similar."
Is Health Canada the regulatory body that operates in Canada?
Correct. Yes.
Yeah.
So, it'll be interesting. It's definitely an interesting response to what we've seen inside of China, where they have these really rapid response times for feedback on clinical data and moving forward. This is a very interesting tactical response from the US.
Yeah.
For sure.
Yeah, I'm so far removed from like anything that's, beyond the cell biology, basically. Yeah. So when I hear things like, oh, the regulatory landscape is changing, I'm just like, even that sentence was probably like stupid.
but overall, right? Like this, I think this is going to be really important when we think of early stage companies now coming in. How are they going to be approaching their clinical trials given this sort of news? In some ways, I think this will reduce the cost, the burden for getting a clinical trial off the ground, because you wouldn't have the same level of man hours that are required to be constantly updating and submitting forms in a very specific way to the FDA. You see something quite a bit different.
Sure.
So we'll see.
Yeah, and speaking to that, it's a little bit off topic, but I saw a chart today that was talking about the use of AI in healthcare, and it had like the different pillars, like regulatory submissions and things of that nature, internal like filing, drug discovery, and like wet lab. And wet lab was like 1% report to use AI significantly in wet lab scenarios, but it was like 83% for regulatory submissions and stuff like that. So that pillar has already been being, we're trying to crack the egg there. To like that seems to be the one area where it's like we can really make some progress here with some better software.
Exactly. Yeah. Cool. All right, so we're just a couple minutes away here from John Boyce coming on the show. Excited for that. So again, John Boyce, really well known inside of the early stage biotech space. Has seen some really cool. Has seen quite a lot inside of the space from an investment standpoint. So we're looking forward to getting his thoughts on where the puck is going from a biotech perspective. So
lots of hockey references today. You watching the playoffs?
It's in my blood. I'm Canadian.
Let's go Sabres. Yeah. Any news on where he might be? Oh, well, I heard a sound.
Yes. So, ladies and gentlemen,
we present you
with John Boyce. John, welcome to the show. Can you hear us? John, can you hear us?
Hello, guys.
Yes, you're here. We can hear you. Can you hear us? Stand by, folks. We've got some technical issues. John, can you hear us? Hello.
Is he frozen? Uh-oh.
It'll no, that didn't do it. Oh well.
Oh gosh.
We'll keep John in the middle. All right.
I think he froze out.
Did he freeze out? All right. Well, we can give him if we go like that for just a second while John figures out what's going on. Yes, so I guess without any further ado, pending the internet working well, we're excited to have John Boyce on. I first met John a couple weeks ago at oh no, not several weeks ago. I first met him when I was working at Nanomosaic. And he was one of the investors of the company at that time, and so he's seen some pretty cool stuff inside of the space. Been able to stay inside of the biotech area for a long period of time. So we look forward to having a chat with him once the internet connection gets sorted out here.
I'm seeing something interesting here that we can maybe talk about while we wait.
Go for it.
I'm trying to kind of piece this together myself. So I'm seeing it on LinkedIn here. Am I still sharing my screen? I think I am.
No, I can't see it.
I'm not. Yes, I am. Where is it? Oh, here it is. Okay, so this is this was just posted by a woman named Susan B. Nichols.
Love Susan.
You know her.
I do.
Okay, well, this is actually a really interesting take here. So Lilly just licensed some stuff from ProFluent. We talked about that today.
Yeah.
Right? Well, they recently acquired Orna Therapeutics, obviously, circular RNA-based company. Colonia, which was a in vivo CAR company. And now they're getting ProFluent. She's saying that these are connected somehow. Let me think here, because I don't see how they're connected.
Yeah. Anyway, John has returned to the studio. So we can do that.
Perfect.
Excellent. All right, John, let's see here.
Things out of my...
Can you hear us?
Do it again.
Here we go. Hey.
We can't hear you.
All right, guys. I'm back. I pulled a bunch of wires out of my computer. I don't know what I broke, but I get sound back, which is a good thing.
Hey, right on. Excellent. Well, John, just to get started here, could you introduce folks who you are and what you do?
Certainly. Thanks, Ben. I'm John Boyce. I'm a serial entrepreneur. I've done a number of companies in genomics, proteomics, and I'm a fellow at Harvard. I teach entrepreneurship and innovation. Class has grown from 8 to about 420, so it's gotten quite large. And I am also a venture capitalist, started a venture capital fund called 28 Capital. So seeing a lot of cool things across the industry, which I talk about with my friends Ben and Jeff quite a bit about. So always good to bounce
do,
things off you guys as well.
We do indeed. So what are you seeing now, John? What is 28 Capital mainly focusing on, like gene therapy, the gene therapy space, or are you kind of dabbling in different areas? Oh no,
I'm in different areas, Jeff. We're gene therapy though is definitely going the interest in a huge way though, and certainly we're in the ADC field, we're in the therapeutics field and immunology. Although there's gene therapy is something specifically I have a big interest in because I think it's a field that can come back in a big way if you can actually fix the tech stack that's holding, I think, the company back, because the science hasn't failed, but just the infrastructure hasn't caught up. And I think that's the stage we're at right now. And fixing that tech stack, I think, will bring things along quite nicely, starting from analytics, first and foremost, figuring out what you can measure and are you measuring it correctly. Doing that, then fixing the retargeting, the safety, and then the manufacturing aspect of things. So doing that then gets you to a broader range of applications other than just rare disease and more into common disease.
So you're saying it's both molecular, like the actual biological, the biological aspect, and also like the in real life manufacturing aspects both need some upgrades?
You got it, my friend. You got it. So starting first and foremost, the first is the analytics. What are we actually measuring in order to fix that? So if you're going to fix things, you need a tool to actually measure, to figure out what's ground truth. And quite honestly, what's happening in the field in general, for a long time, just starting with the analytics portion first, we just got FDA approval for one of our companies, Nanomosaic, for the AMT status designation, for the only technology in the world now the only technology that actually has AMT status designation for measuring full versus empty versus partial capsid. So what does that mean, basically? For those who aren't familiar with gene therapy, you have a capsid that's empty. It's not going to do anything for the patient. There's no message contained within it. You have a capsid that's partially full. It's a half empty message, and it's not going to really do anything for the patient either. If you have a full capsid, a full message in there, that works. So currently people use digital PCR to measure the transgene, and they use another methodology to measure the capsid itself, and then they try to normalize across different platforms. And you're comparing two different platforms with their own inherent biases, trying to normalize across that. And then you can't really measure the partials; those are counted as full either. So you get this really wonky results. And what we're seeing is that a lot of these companies out there, even large pharma that aren't using the system, are basically saying we're 80% full when in fact they're only 30% full or less, 20% full. And
they're not lying. It's just that their methodology to detect it is not sufficient.
Yeah.
You got it. You need exactly. And they're doing the best they could with the tools they have. And that was ground truth for a while. Everybody has their own normalization methods, and they're working their best to get the safest medicines out. And it just wasn't. You just needed to have one system that measures both nucleic acid and protein on the same chip at the same time in order to cross those barriers and actually to get the partials out on that. So analytics check mark. We've got a good check on that. We can actually measure potency as well, which is great. The next question then in gene therapy that needs to be fixed is the manufacturability, just as you were mentioning before. So quite honestly, if you wanted to dose of let's take Zolgensma, cost of manufacturing that is roughly like $323,000 a dose for Zolgensma. If you have a producing cell line, AAV producing cell line that is designed correctly and effectively, you can get that cost down to about $1,032. And we've actually shown that we have technology that does that on the profile. So to treat the whole population for Zolgensma, if you look at 3,000 patients, you're taking the cost down from roughly $950 million, $960 million total, down to about $3 million to treat that entire population. So all of a sudden, you see it gets much, much better on that side of it. So
that's okay.
Yeah, no, that has definitely just been the Go ahead, Jeff. Sorry, go ahead, John.
Go ahead. I'd love to hear your comment.
Yeah, like again, that's kind of been the challenge inside of gene therapy so far, right? Is the cost per dose has been so high, and we've kind of been using this tech stack that, for the most part, has been around since the 1990s, and there have been some improvements along the way. But yeah, I see as you do, I see a lot of really interesting technologies that are coming on board to now meet that need that will ultimately have a pretty significant impact on bringing back gene therapy. I agree. The gene therapy is poised for a bounce back.
I absolutely think so. And now's the time with my investment hat on. investing in technologies that fix that tech stack, I think, will be, because then owning that puts you in a good position to make safer medicines, not just for rare disease, but for more common disease. So like starting to think about like retargeting in cancer. Can you actually retarget gene therapy for cancer and make it safe? And we published in Molecular Oncology in 2025 that we could attach AAVs to nanobodies, and we could actually attach them to full-length antibodies as well. And can you actually use it? It's kind of like a horse and buggy model. Like, in other words, the horse is going to pull the buggy, which is your capsid, directly only to what you're targeted to. So to being able to do that effectively and retarget and without the capsid falling apart, we've shown that we can do that by delivering 85x more message to the intended target, as opposed to traditional gene therapy with AAV2 and AAV9. We haven't published AAV9, but we show the AAV2. And then actually 45x times less to the liver. So safer, more efficacious medicine directly targeted. And what we haven't shown yet, and I'm announcing on your show here, which is actually interesting, which we should be publishing soon, we've shown that we can cross the blood-brain barrier with targeting nanobodies onto capsids in a very specific way, and transducing across the blood-brain barrier as well. So that is actually, I think, the next step when you start thinking about CNS and for gene therapy. This is great in that tech stack. So again, getting that tech stack fixed with the retargeting, manufacturing, and the analytics, I think gets you to a good spot to start going after not just rare disease, but common disease as well. So when I think of platforms, I hear platforms. Some people say we have a great therapeutic platform. We get a lot of these things coming across. And yeah, it can be a great therapeutic platform, but there's still the issues of the tech stack we talk about, the CMC, the manufacturing costs, all those things still exist. Until that gets fixed, I think, I don't want to say you're in a holding pattern, but the infrastructure has to catch up to the promise of what gene therapy can deliver. So that's, and what we've seen that it can deliver. So fixing that, I think, is
So one of the biggest, I guess, advancements that you're saying is going to allow gene therapy to go from like monogenic rare diseases into more common diseases is the targeting methodology. What do you have to say about the different types of like actual payload technologies? We're seeing a lot of interesting things come in terms of, I don't know if this is relevant for AAVs, but in terms of things like new recombinases or new CRISPR systems or new types of like mRNA technologies. What do you think? Do you have any thoughts on that aspect of the technology?
Like targeting, like putting, like conjugating on, say, like different oligos or different mRNAs to the capsids. Is that what you're thinking, Jeff? Or
no, I mean like the actual payload itself, the technology associated with the actual like nucleic acids themselves.
Okay, yeah. So interestingly enough, I mean, because when we conjugate an antibody onto the AAV, we call the AAV the actual payload. Actually, we
okay.
But you can do different payloads onto different, like, say, nanobodies or you could take oligos or siRNAs and conjugate different payloads on those. We've seen some interesting dynamics come out. We've seen some of the payloads coming across in ADCs now starting to make their way into molecular medicine on terms of the siRNA side. We've seen some very funky conjugates that have come up that actually have like exatecans and direxatecans on them, which you normally don't see. So we're seeing a sort of this explosion in it outside of gene therapy, but more basically on this explosion of sort of cell-free therapeutics, as they're calling them. It's an interesting new wave that's certainly coming across. A lot of promise behind it, but again, I'm a believer in that as well. But I'm also still a strong believer in the gene therapy side and getting that tech stack fixed and moving that along.
Right on. So yeah, John, I guess just with regards to like where you see the puck going as well, and the investment thesis of 28 Capital, like what outside of gene therapy, are there specific areas or technologies that you're interested in looking at over the coming months or years?
Oh, absolutely, certainly. There's certainly the proteomic field. We've done a lot on that side of things. We've done a lot in the antibody drug conjugate side of things as well. I still think ADCs are hot. There's new methodologies and new technologies that will improve the ADC side of things, from payloads to linker technology to really, I still think, again, the tech stack, even in ADCs, the conjugation technology can make things a lot better, being able to go wherever you want on the antibody or the nanobody in any way, shape, or form without any restrictions. Because specificity does matter. So that is something that is important to us. So we've actually looked a lot into the ADC side of things. And then, of course, outside of that, there's the AI aspect of things. Everybody's always talking about AI, but where do you apply AI to? There's drug discovery, which is always very interesting. But we've seen things in terms of we're looking at improving clinical trials. So how do you actually improve clinical trials? And there's a lot of different technologies that are out there. We're under NDA now, looking at and trying to figure out which actually will do that the best way. But using AI to do that, so you can cut down on the size of the clinical trial, or basically even obviating clinical trials, and to move things a lot faster, to get a first pass in terms of figuring out how it have response before recruiting your patients. So
I'm sure that
there's a lot of interest in that. So again, all along development.
Yeah, I'm sure that so me and Ben were just talking about the this new real-time the FDA kind of.
Can you guys hear me?
Yeah. There's a little bit of a lag, so we might the responses are a little bit.
I'm losing you, Jeff. Sorry.
Oh boy. Ben, can you hear me?
No, I didn't tell you guys. I'm calling from the moon. This is I'm in the space station right now. This is why they're not.
Yeah, exactly.
That's all right.
How's the view up there in space?
On the far side of the moon right now, guys.
It's just like, wait for it, wait. And then it lands.
Nice. Well, John, we appreciate your time. We know you're a very busy man. We'll probably wrap up the show there. Thank you for coming on and sharing your expertise. We're looking forward to well, at least I look forward to seeing you at ASGCT. Looking forward to catching up, and excited to see where the space is going to be going. And thanks for providing your perspective. We really appreciate it.
Thank you, guys. And last thing for all your viewers too, if anyone we are the night before ASGCT starts on Monday, May 11th, we are hosting an event at Goodwin. Of course, Ben and Jeff, I hope you guys are there for that too. So it's from 5 to 8, sponsored by Goodwin. Anyone wants to come to the event, it's a social hour that the panel will have put together. Hit my LinkedIn, and the registration details are on that. It's filling pretty fast, but get your name on the list, and you should be able to get in. Excellent.
Awesome. Thanks so much, John. We appreciate you. If you can stay around for just 1 second, we'll make sure that your video uploads, and then we'll let you go.
Thank you guys again. Really appreciate it, guys.
All right. Well, thank you everyone else for coming today, and we'll see you next time. Signing off. All right. Cheers.
Thanks, guys. Sorry for the technical difficulties. It's different. Okay, take care, guys. Bye, guys.
Not a problem. No worries. All right. And we are out. Thanks again for coming, everyone.